So, right, my name is Mark, and I'm going to tell you about this Cosmic Spiderweb. Most of you have probably heard about the Cosmic Web, and actually you can add the word spider to web, it turns out, which hopefully will make a little bit more sense after I give this talk. Right, this workshop is supposed to be about analytic methods, and I'm actually not, well, the word analytic can mean several things, but I'm not actually going to show many equations, but I am going to talk about a formalism that's very elegant for understanding the cosmic web. So when I was in graduate school, I thought of an n-body simulation as some horribly complicated thing that happened, some nonlinear. It is nonlinear, but it's something that you feed in some initial conditions and it does something really complicated and you get some stuff out which is sort of related to the initial conditions, but it's actually, but it is not super understandable. But since then I've realized that a lot of the stuff, at least on large scales, is surprisingly simple. And a lot of this comes through the adhesion model. Okay, so the connection to the word analytic, the adhesion model is arguably, depending on the definition of the word analytic, it's sort of an analytic formalism. It's actually a geometric formalism. I don't know what a formalism is, but I guess it involves formulas and so instead of dealing with equations, I'm quite a visual person, so the geometric nature of the adhesion model appeals to me. Okay, so I'm going to describe this adhesion model and how it leads to a structure that is equivalent to what's called a spider web in architecture, which has some possible cosmological use. And I'm going to say some other stuff at the end if I have time. So, right, the Zldovich approximation is probably the starting point of this, as it was for actually a lot of modern large-scale structure research. Okay, the Zldovich approximation is what's used to make the initial conditions of cosmological n-body simulations. It's a deterministic mapping. So these variables, this is, I think, the only equation that I'm showing. So this x is the Eulerian actual position of a particle where it ends up. So this is for, say, a particle or a vertex of a mesh, as I'm going to show in a bit. Q is the initial position in comoving coordinates of that particle, and this thing encodes the displacement between the initial and the final position. So this is a gradient of a potential, and the potential is important. It's basically the gravitational potential, at least to linear order. And this d quantity in the Zldovich approximation, which is a linear theory, this just grows with the scale factor. Or sorry, not with, well, in a matter-dominated universe it does, but this is the growth factor, which just scales with time, constantly everywhere. So in reality, the displacement between the initial and the final coordinates is more complicated than this, but this actually does surprisingly well. So I'm going to show some examples of the Zldovich approximation. So so some of you have seen these before. I've had these for a few years, but I think it's pretty cool. So this is something that looks kind of like a two-dimensional universe. So we have some kind of mesh. So here it's a square mesh, and we have some initial conditions, which, and here you might be able to see some small shading here. There's some green patches and some blue patches. And the blue patches are where it's denser. And in the Zldovich approximation, these vertices of a mesh move around, and in places they cross, And this stuff that forms here is the cosmic web, essentially. So where these patches were initially in different places and now they're in the same place, which is something that only dark matter can do fully. So in the gas in this situation would also collect in these places, but it would collide and do something different. In particular, do things like form stars and galaxies. If we take this Zeldovich approximation too far, it goes crazy. but at least for mildly nonlinear scales, it actually does pretty well, which I'm not actually showing there, but this looks sort of like an n-body simulation. And you can also do this with other things like, whoops, I guess I should. This is the Mona Lisa, which is nearby, kind of. And you can use any sort of pattern to distort this mesh. So it uses as the initial conditions of the universe. So that's kind of interesting. Some filaments form it. And here's a nearby dome in the Pantheon. So that's kind of fun. There's kind of a face that forms there. It's just an accident of the angle of the picture, I guess. Okay, so in the Zeldovich approximation, we get these so-called streams that pass each other. I guess I should. And the way that so in this approximation, these streams just fly past each other ballistically. But in full gravity, something arguably sensible happens. These patches form collapsed structures. So this slide is an attempt to convey the phase space structure of what's going on when patches collide with each other. So this is a gravitational simulation run with the cold dice code that Stefan Colombi and Terry Sousby wrote. It's a very nice code that actually treats the dark matter as residing on a mesh that deforms sort of like what I was showing before, and it adaptively refines this mesh where it needs more resolution, in particular in collapsed structures like halos. So I applied this code to a perfectly compensated void, which you may be able to see kind of. There's a ring here that has higher density than the mean, so that the mean density in this two-dimensional universe is out here. There's a higher density here, and there's an underdensity in the middle. So this is a perfectly compensated, meaning the average density within this ring is the mean void. And what's on top here is a view of this sheet that's in phase space, the position velocity phase space. So the xy coordinates are just this sheet put through the screen. And the height here is the velocity. So this is circularly symmetric, so there aren't actually two separate components of the velocity. It's just the radial component of the velocity. And when this runs, this happens. These colors here are just meant to show you where different patches of the initial sheet end up. So you can see a few things here. One kind of cool thing that comes out here is that this is a kind of perfect cone, or it looks like it at least. So these lines here are straight, and that actually just tells you that there's a sort of a Hubble law going on inside this void. So as you go out some distance, the velocity that you get, the radial velocity from that point, is just proportional to the distance away from the center, so that you get this Hubble law that's a straight line. But that's a bit beside the point here. What I'm trying to show is this curly structure here, which in a one-dimensional universe looks like this. So the reason that you get this spiral structure in phase space is that from each direction you get velocities that are oppositely have opposite signs when there's a lump in the middle of the universe in one dimension, and something that happens here but not in the Zeldovich approximation is that these things curl up. So that's just sort of a harmonic motion. When patches come to this overdense region, they stop and go back and forth, whereas in the Zeldovich approximation, they fly past each other. Okay, so this is a two-dimensional simulation run by, well, it's a two-dimensional Zeldovich realization done by Johan Hidding, who's responsible for much of the first part of much of this work. A student with Rien in the back, and so this is essentially one of the Zeldovich realizations, like I was showing interactively with the Mona Lisa and so forth, except also it's shaded according to the density. So you see that the density out here is low. These are voids, and in here they're filaments, but these things become quite fat. This is the Zeldovich approximation. Things fly past each other unrealistically. But the adhesion model is a formalism that collapses these things into these lines. And the way this works, which I'm not going to go into great detail well, I'm not going to explain in great detail, is that you put in a viscosity into the dark matter, which we don't think actually has dark matter. We don't think the dark matter has viscosity, but you put in a viscosity into the equation of motion, and then you go through some formalism, and then take the viscosity to 0, and you end up you end up being unable to make these fat structures that fly past each other, which so I didn't explain in great detail how that works, but one intermediate step to the geometric thing that I'm going to talk about is this parabolic thing that emerged from the work of Pogosyan and Kaufman and others. So the way this works is, okay, this is a one-dimensional universe. You probably have little idea what all this stuff is, but this black curve is the potential. So you expect that in potential wells you get structures forming, and where the potential is high you get a void. So the way that you map from the initial conditions to the final conditions is to put these parabolas on this and connect neighboring points by parabolas. The apex of each parabola tells you the final position of the patch of matter that was between those 2 points. And so that works kind of simply out here, where the parabola just barely grazes the potential, but in a place where the potential is too deep to accommodate this parabola, which has a finite width, then you actually get this whole thing collapsing together, and the whole thing ends up at the apex of the parabola. And it has a relation to Legendre transforms, and in particular, and this is something that Johan realized, is that it's equivalent to what's called a sectional Voronoi tessellation. So probably many of you are familiar with Voronoi Tessellations, but I'll say briefly what they are. So a Voronoi tessellation is a tessellation of space into tiles or cells, such that each cell is the set of space that's closest to one of the generating points. So you have a set of generating points, and basically the closest patch of matter or space to each generating point is its cell. Now it's possible to generalize this process, and I'll show you a little example of that. So this is something that looks a bit like the Eiffel Tower. This will come back. So this is a Voronoi tessellation based on these blue generating points. So the black stuff is Voronoi tessellation. So here, this trapezoid here is the set of space that's closest to this blue point. And similarly for these other cells, these cells go off to infinity. And it looks a bit like the Eiffel Tower. So this is a bit small, but I think I can shrink it. So these green points are an interface to change the weight in each cell. So I can actually slide the lines in and out according to this weight. It's an additive weight that basically changes the distance that you use to calculate the function that you use to calculate the distance to that point. So by changing that distance function, you can make these cells bigger and smaller. So you can do some weird things there. And you can even make these points disappear. So if the weight is so small for a given point, there's no patch of space that's by that point's distance function closest to that point. Okay. And it happens that in the adhesion approximation, you also use this sectional Voronoi or power tessellation to produce the realization. So this is actually quite a simple technique. So usually in the Zadovich approximation, we use a fast Fourier transform to produce a displacement field from a density field. And we just move particles or mesh cells according to that displacement. Here, actually, instead of doing that fast Fourier transform, we use a sectional Voronoi tessellation, which is more computationally intensive a bit, but conceptually it's not really any more complicated. In fact, I argue it's actually could be a little simpler. And what happens in this Voronoi tessellation, so this is probably completely mysterious on the left, but here you get a cosmic web developing at right. So what happens is that you start with a uniform mesh where there's the same amount of matter in each of these cells. And based on the potential, the different cells move in, or sorry, either grow or shrink according to this weight in the Voronoi tessellation. So actually, the generators remain in the same place, but the potential changes. So the potential is 0 in this case, but it grows with time, or it gets linearly scaled with time. And you end up with some cells that are quite big, where the potential is large, and some deep potential wells, where you actually have these cells disappearing from the tessellation, and the mass gets deposited in a certain place. And there's a wonderful interactive code that Johan made, which I'll show you. So I honestly didn't really understand the adhesion model until I worked with his code. at least not its elegance. So what happens is you start, so this code is at, well, I'll come back and give you the link if you're interested. But what happens is you start with a density field, as we always do in cosmology, kind of, and that gets transformed with an FFT to a potential field. I guess you could also alternatively start with a potential field. And so the potential is a smoother version of the density field. It's attenuated by a k-squared factor in Fourier space. So you get some big blobs and bigger blobs than in the density field. And there is a, so this may be a bit confusing, but this is a two-dimensional version of the one-dimensional set of the paraboloid graph that maybe is already confusing in one dimension. But what we have here is a bunch of lines and a bunch of points. The points are places where the potential is sampled, and the lines are come from this tessellation. It's actually the dual of this Voronoi Tessellation, called the Domani Tessellation. And maybe you can see that some places the red points are attached to the lines, and some places they come up off of the lines. So these places where the red points come off of the lines are the potential wells where the matter is collected. And maybe, so for example, there's, well, so you actually have a paraboloid that you try to put into these potential wells, and if you can't fit that into the potential wells, then that's a place that's collapsed. Okay, I hope that helped a little bit and wasn't just confusing. But this is what I really wanted to show. This shows. Oh, okay, right. The red points are just places where they're points of. Okay, yeah. I didn't say what the space was or anything. This is if you view it from the top. This is Lagrangian space in a two-dimensional universe. So if we project it all the way through, so the red points are just Lagrangian points, or Lagrangian, not orbital Lagrangian points, but Lagrange points, but they're just places sampling Lagrangian space, and they have some potential, which is the height of this thing. Yeah, this was probably not worth explaining, but right, the height of this is just the potential, and this is you try to.
This meaning the red points or the black?
It's the red points are the potential, right, and the red points are the potential, and the black lines are a construction that comes from trying to fit paraboloids into these potential wells. Okay, I'll just move on from that because I don't think that's super helpful. But what we have here is a cosmic web in Lagrangian and Eulerian space, and we can just maybe see what happens when we change the scale factor. So here we're moving time backward, and things are becoming more homogeneous. These cells are becoming more homogeneous. So eventually we end up with the regular grid. And so you can kind of see maybe how this develops. So it's probably still mysterious what's going on at left. So here, this is in Lagrangian space. So this is the space of the initial conditions. And the little triangles here are volume elements that remain uncollapsed. So these correspond to these gray lines out vertices in these gray sections here, these voids. But when structures form, these elements actually merge together. So this is what happens when you have a paraboloid that you're trying to fit into that set of red points, but it doesn't fit. These triangles merge together into a larger Lagrangian cell. And those become the red and blue parts of this Eulerian cosmic web. So like these, and the bigger the cell is, the more mass has accumulated into that point. Okay, so I hope that was kind of understandable. It helps a lot to look at this code. It's actually very simple. It just involves a potential and sectional Voronoi tessellation, which probably isn't immediately familiar to you, but it's not so complicated. All right, so I think that's the end of the interactive stuff. I'll skip that. So maybe it could be a bit helpful to look at what happens in this case in 1D. So in 2D it was a bit confusing. It's also probably a bit confusing in 1D. But I'll show you how a one-dimensional cosmic web comes from this potential in this case. So here we have a potential. So we expect, again, that things will eventually form at potential wells. And so, okay, we start with this Voronoi tessellation, which in one dimension is just a number line with equally spaced lines. So here the potential, the weight in each of these cells is 0, but as we start to introduce this potential, we have these cells change in size. So this is actually a two-dimensional Voronoi tessellation. The reason why this is called a sectional Voronoi tessellation is that it's a slice through a higher dimensional Voronoi tessellation, where we actually lift some of these points according to the potential. So actually in potential wells, we lift these points away from the x-axis, this orange line. And eventually, these lines get lifted in potential wells so far that their cells cease being attached to the x-axis. And that tells you that that they have donated their mass to neighboring regions. And so all of this stuff that has departed from, whose cells have moved away from this line, all have collapsed in this broad, these broad black lines. And well, you can see that in a potential hill, you get some widely spaced cells, and those are low density regions or voids. Okay, so hopefully that was a bit useful to understand. Now I'm finally going to talk about spider webs too. So actually sectional Voronoi tessellations appear in architecture as well. So here's something I saw at LAX a couple months ago. It appears to be, at least to me, a sectional Voronoi tessellation. So a spider web, which is something, well, of course, a spider web is a web that is made by a spider, but and this is an actual web that's made by a spider. It was made by an artist, Thomas Saraceno, who's actually doing an installation mainly of other things than spider webs, but I think also maybe some spider webs. He's installing something at the Palais de Tokyo in next month. So I'll try to see if there are any events going on with him, and let you guys know if for people who are going to be here for that. Anyway, so this is a spider web made by a black widow colony. It looks a bit like the cosmic web. It doesn't look quite like the typical radial set of polygons that there's an emoji for example. And this has architectural value, of course. That's why they build it. And well, here's another thing that Thomas Saraceno has made. This is an installation where he scanned an actual spider web that similar to the last thing and blew it up to room size where these people can sit. And he does make he has made the assertion that this looks a bit like the cosmic web. So this 14 billions refers to the age of the universe. And this working title is actually part of the title. It's not that 14 billions was the working title. And the reason that that's part of the title is that he wasn't sure if this really had anything to do with the universe or not. He just thought it looked like it. And so he didn't want to make the connection too strong, but actually, based on the work that we did, there is a strong connection. So, okay, I'm going to go back to physics now, or statics actually, which used to be more taught in physics. So in structural engineering, there's a way to analyze the statics of a set of, like a truss work of beams and tension cables. So here we have a weight, or a briefcase, I guess, that's hanging on a lamppost, and we can analyze the forces on it. So there's some force leading, well, in this direction. There's a compression in another direction, and there's the weight. And if this is an equilibrium, this makes a closed triangle. Sorry that this seems a bit disconnected from what I was talking about. Hopefully it'll come back. So actually, James Clerk Maxwell, who we know better for other reasons, thought of rotating this triangle, which is not profound in itself, but as a way to analyze whole networks of these things. So again, this is called a forced polygon. If we go to a network of these things, a bit like the Eiffel Tower, again, we end up with several nodes. And forget for now what this black thing is. I'll tell you what it is. But something is called a spider web if it can exist entirely in either tension or compression. So either because you can reverse the sign of the tension or the compression, and it ends up working. So here, well, of course, the Eiffel Tower is roughly in equilibrium, and it's all in compression. It's all weighting down on itself. Similarly, you could reverse the signs and make the Eiffel Tower out of threads of spider silk or tension cables. And okay, back to what Maxwell did. So at each of the nodes of this network, you can make a force polygon, again, where each side of the polygon tells you the force going in the perpendicular direction. And if everything is in equilibrium, all these force polygons fit together without any gaps anywhere. So each of these, so like this vertex of the form diagram, as it's called, or the actual spider web in space, corresponds to this triangle where the length of this member corresponds to the force coming off in this direction. The Voronoi, so this actually relates to Voronoi and Domani tessellations. These are dual tessellations. So in Maxwell's language, these were called reciprocal duals, where one tessellation is perpendicular to the other. That's kind of the definition of a reciprocal dual. So you can actually always make one of these things out of a Voronoi tessellation of objects. And actually, the general set of these things is just a little bit more general than these Voronoi Delaunay duals. They're actually the sectional Voronoi Delaunay duals. So okay, I realize that I'm running out of time, but I'll say just a minute or two more. So what sort of thing is not a spider web? So because the cosmic web is built out of the same structure, the cosmic web it seems to be a spider web, but what is not? So one example is this green thing. If all of the threads in a network are pointing in the same direction, and all of the forces have the same sign, that's not going to be in equilibrium, obviously. You don't have a balancing force on the other side. Also, if you have something that looks like a truncated version of the Eiffel Tower with just one triangle here, if you tilt one of the strands, so if gravity was going, so in this case, if gravity was going in a diagonal direction, then you wouldn't be able to close this force diagram, and it would not be in equilibrium. Okay, so there are a couple of papers that proved that in 2D, spider webs and sectional Voronoi tessellations were equivalent constructions in 2D. Actually, in 3D, it's not quite that simple. So in 3D, a sectional Voronoi tessellation, so that's what happens in cosmology, a sectional Voronoi tessellation, is a spider web. But there exist spider webs in 3 dimensions that are not completely sectional Voronoi tessellations. So the equivalence isn't quite as simple in that case. So let's see. So actually, this correspondence came through the small origami literature, which if you're interested in that, here's a link, Ling and Bateman 2011, which is hard to find. You can ask me about that. Okay, so in the last couple of the last minute, I'm just going to show something that I made based on the Council of Giants, which is a name that is not really cut on for the closest several galaxies around the Milky Way. It's a roughly 2-dimensional structure, which is possible to represent in 2 dimensions, conveniently in both origami and also as a spider web, or a sort of a dream catcher thing. This has the same geometry. And okay, just very briefly, something about the cosmological use of this. And this will be the last thing I say. So I mentioned that these things were perpendicular to each other. These things being the Voronoi tessellation, which is the set of filaments and walls in the universe. So here we have some polygons that are a Voronoi tessellation. So this is an extremely idealized large-scale structure set of observations where we just see some Voronoi cells. And the Domani graph between the generators of these points, these things are perpendicular to each other. And if we had the wrong scaling in a set of large-scale structure observations in a galaxy survey, then and we were observing in real space, which is, of course, not what happens. But if we were able to view it in real space, then there would be a shear in one direction, and these things would cease being perpendicular to each other. So if we could perfectly reconstruct the centers and the centers of these cells and where these cells are, we could test for whether these things were perpendicular to each other, and in principle do something like an Alcock-Wachynski test, looking for distortions in one dimension relative to each other, to the other directions perfectly. Now, of course, we can't do that perfectly, but if we were so this is a 2-dimensional correlation function that I made from this, which so the blue stuff is the correlation function here. Well, of course, it's not. What we're trying to do here is to match the blue contours of the correlation function to the orange radial arcs, or circular arcs, And it's more difficult to optimize the fit of these blue things to the orange things than it is, in principle, in this idealized case, to look for perpendicularity, I would argue. Okay, so that is it. I'll just stop there. Thanks.
Thank you. Thank you. Time for some questions before we go to coffee. The cosmic waters. At the back of the room, questions, comments.
No, I mean, no, why? I mean, it's, I was just your joke about coffee, which I think.
I was hoping you were going to comment on the web. Go ahead.
Just, can you put up this slide again? I didn't get what the orange balls are.
The orange dots. The orange dots are generators of these Voronoi cells, and are roughly the potential maxima in if these were voids, these would be basically the centers of the voids or the potential maxima.
So then your point is that the lines connecting the centers of the voids are orthogonal to the wall of the void.
Yeah, they're orthogonal to the wall of the voids, the walls. So I am glossing over something here, which is that this spider web within a void. So of course the filaments that we observe in the universe are not perfectly straight, as you would expect in something like an architectural set of beams. And a physical filament can be bent and curved, and that is achieved in the spiderweb construction by putting some thin tendrils within the void, actually. So yeah, so I glossed over that. So what's relevant here is that the correspondence between this Voronoi cell and a void built of many cells is only approximate. But sorry, maybe I didn't.
What changes between the
between the top.